Okay, the Haber process. First question. Name one source of methane. You're not allowed to say my nan. You won't get the marks. The correct answer is natural gas. Okay. Next question. Air is the source used to produce nitrogen. Suggest why air must not get into the reactor. Okay, so you're mixing nitrogen and hydrogen in the reactor to make ammonia. But some nitrogen and hydrogen survive the process and come out as well. So what was the question? Suggest why air must not get into the reactor. 2 marks. Well, air is 21% oxygen, okay? And you can't let oxygen get into the reactor because it's going to react with the hydrogen, okay? So oxygen is going to react with the hydrogen. The oxygen could also react with the iron, which is the catalyst, okay? So you don't want that to happen. You want all the hydrogen to react with the nitrogen and nothing else. Okay. Describe what happens to the mixture of gases from the reactor. 3 marks. Right, so like I said, some of the nitrogen and hydrogen survives the process and some ammonia is successfully produced. Okay, so what happens to these gases? Well, the first thing is that they're cooled. Okay? And the reason they're cooled is so the ammonia condenses. Okay? So the ammonia condenses. And it's separated from the nitrogen and hydrogen, which remain as gases, just by tapping it off. Okay? And the nitrogen and the hydrogen are recycled back into the reactor. So these two, they're recycled back into the reactor like that. This is a continuous process. The Haber process, the reaction, it's a continuous process. That means the reactor is always running. It's continuously making ammonia. It's not a batch process. And so the nitrogen and hydrogen that make it through the initial reaction, if you like, that's why they're recycled back, so they're not wasted. Okay, so those are the 3 reasons, 3 marks. Okay, this graph. Use the graph to suggest the conditions that produce the greatest yield of ammonia. Okay, so yield y-axis, pressure here, the conditions that produce the biggest yield. Well, here, at that point there's no higher yield on the entire graph. And so the conditions are 200 degrees C and 1,000 atmospheres. It's only a 1 mark question. Okay. Right. Use the graph to suggest and explain why the conditions used to produce ammonia in the Haber process are a temperature of 450 degrees C and a pressure of 200 atmospheres. Okay, this is a classic exam question. You have to explain why these particular conditions are always used in the Haber process, despite the fact that with lower temperature, for example, you can get a higher yield. And also with increasing pressure, much bigger pressures, that also increases the yield. Okay, well, I've written out the textbook exam answer here. So just remember this, tattoo it on your brain, commit it to memory, and just regurgitate it in the exam, and you get maximum marks. Okay, well, let's look at the conditions. 450 degrees C, it's somewhere between these two here. That's 400, that's 500, and 200 atmospheres. Well, there's 200 atmospheres, and there's 400, there's 500, so we're about there, okay? Apparently, for some reason, that's the best point to choose to do this reaction. Okay, so 200 atmospheres, it's about 25-30%. I haven't drawn this brilliantly accurately, but on your exam question sheet, it comes out at about 25% if you read across there. Okay, so in the exam, first thing to do is write down that N2 plus 3H2, double arrow, goes to 2NH3. The double arrow meaning it's a reversible reaction. That's very important. And remember, it's exothermic in the forward direction and endothermic in the backward direction. Okay, don't write the numbers, but write everything else in nice, neat sentences. So the first thing to write is the reaction is reversible. Okay, and then the next 2 points deal with temperature. The forward reaction is exothermic, so decreasing the temperature increases yield. Okay, we'll talk about the reasons why at the end, but just write that down. It's true that whenever you decrease the temperature, okay, it pushes the reaction in the exothermic direction. And in this case, exothermic direction is the product we're trying to make, so that's the yield direction, if you like. Okay, then say, however, decreasing the temperature also decreases the reaction rate, which is a bad thing. You want a high reaction rate. Okay, so that's dealt with temperature. Next, 2 points of pressure. There are 4 molecules on the left, but 2 on the right, so increasing the pressure increases yield. The 4 molecules on the left, 1 nitrogen and 3 hydrogens, but on the right, there's only 2 ammonias, so there's twice as many moles on the left as there are on the right. However, high pressures are expensive to achieve, and no one likes spending money. And finish it all off by saying the chosen conditions are a compromise between yield, reaction rate, and cost. Use the word compromise, okay? The examiner's looking out for that word. They like that word in the answer. And that's it. Those are the reasons. You've just got to memorize that, regurgitate it in the exam, and you get full marks. Right, the actual reasons why, if you're interested, are as follows. The reasons why this is true. It's actually called after a guy called Le Chatelier. It's based on Chatelier's principle, which you don't need to know at GCSE level in the UK, but I think you should know it. It helps you understand it. Chatelier's principle says that with a reversible reaction, whatever you do to the reaction, it will shift the position of equilibrium to do the opposite. Okay, I shall explain. So, if we try and increase the temperature, it will do the opposite. It will try and decrease it, which means it will send it in the endothermic direction. Exothermic direction is that way, so heat is released when the reaction goes in the forward direction. So if the reaction tries to decrease temperature, it tries to send it in the endothermic direction. Okay? And that's why the forward reaction is exothermic, so decreasing the temperature increases yield. If we decrease the temperature, it will try and move it. It'll try and do the opposite thing. The reaction will try and increase temperature. So if we decrease it, it will try and send it in that direction, because that's the exothermic direction. It will try and increase temperature. So that's why if we decrease temperature, the reaction will increase the yield, send it in that direction. And it's the same principle, Chatelier's principle, with pressure. Okay? 4 molecules on the left, 2 on the right. Think of it like the fewer molecules, the less pressure. Okay? So if we try and increase pressure, say, the reaction will try and decrease it, which means it will send it in that direction because there are fewer molecules on the right. So if we increase the pressure, that's why it sends it in the fewer molecules direction, in that direction. So it increases yield, it increases the amount of ammonia. But like I say, you don't need to know that it's called Chatelier's principle, but Chatelier's principle really helps you with this. So there it is. Job done.